So I'm going to go ahead and introduce Nancy for the audience. So welcome, everyone. It is my distinct honor to introduce our valued speaker for today's seminar, Ms. Nancy Rausch. As a highly recognized professional in the tech industry, Nancy currently holds a role as a senior software manager and data scientist in the research and development division at SAS Institute, steering a team developing SaaS data governance and data quality products. In addition to her commitment to SaaS, she actively shapes the open source tech ecosystem as a chairperson of Linux Foundation AI and Data Technology Advisory Council. Ms. Rausch's influence extends beyond the corporate world, as she also imparts her wisdom to aspiring professionals by mentoring at North Carolina State University. And she is a proactive member of the Laser Institute Advisory Board. Also, she's a prolific researcher with 20 research publications, creating bridge between AI and data management. Today, we eagerly await her insight on the significant subject of data cleaning. But as we prepare to dive into a learning journey with Ms. Rausch, we request that you mute your audio to ensure the uninterrupted session. So rest assured, you will have an opportunity for questions at the end. So let's kindly welcome Ms. Nancy Rausch.
Thank you so much for that wonderful introduction. I am going to share my screen. Can you see my screen?
Yes.
Okay, great. All right, well, thank you everyone for coming to this discussion, this seminar. I'm delighted to be able to share some of the knowledge I've accumulated over the years in one of my favorite subjects, which is data cleaning. Kind of the nuts and bolts of what you have to do when you're working in analytics, but really important as you will see as we get into it. So let's just start with a quick poll. You've heard about me, so this is some of my background. I do have degrees in statistics and engineering and analytics. I do spend quite a bit of time in this space. I do research in various areas as part of my company, and also I do spend quite a bit of time in the university system. Love working through the university. You are the future, and we really want to make sure that those of us who have spent time in this space are able to pass on knowledge and wisdom that hopefully you can use in your future careers. Just a little bit about SAS. We are a very large statistical software company. We have worldwide sales. This is a picture of our campus. Notice the pie in front. We are a lot of statisticians and mathematicians, and we have a pie day that we celebrate. It's a lot of fun. And there's pie served in the cafeteria and all that, because we do get a lot into the deep math around data, analytics, and sort of extracting knowledge out of the data. I want to point out that all the things that I'll be talking about that are around SAS, we do have access for academics to a lot of our SAS software in the cloud. We have something called On Demand for Academics. It's free for academics to use. You will find, as I point out in some of the places where we'll be talking, SAS does a lot of things to try to help automate the hard job of preparing and cleaning data. I use both SAS and Python, and I can tell you that there's a lot of things I'll go back to SAS for, because they just help me do those things without me having to code every single thing myself in Python. But I will show you kind of how to use both technologies in complementary ways. But if you haven't ever used SAS, it's a great way to get in and give it a try. We also offer some great courses. And at the end, I have some more that I'll talk about, but there's some really good e-learning courses that are free. And you can just go to the e-learning site and get them. So you can learn how to use the SAS programming language, which is really handy. If you're an R user, we do have programming classes that show how to complementary use those two languages. And we have a great statistics class, really good foundational area for statistics that you can use that class for. Has some really great examples So if you just need a refresher in statistics, I frequently actually go back to that course myself and play around with things because I find it really helpful just to get that regrounding in those basic principles. Okay, so let's move on to our topic of the day, data cleaning. So here's a poll. How much time do you think people spend when they sit down to do a project, either modeling or reporting? How much time do you think they spend in preparing the data? And you can put it in the chat. I can see the chat. I think we have some very knowledgeable people here. You are right. It's about 80%. And that number actually hasn't moved for many years. Essentially, preparing data is hard. It's hard to find the data you need. It's hard to then use it, get it to fit for your purposes. So clean it and organize it. Even if it's pristine, you may not be able to use it as is. You may need to modify it because you're doing some sort of analytical project that requires it in a different form. Or you may be doing some reporting and you need to flatten it out. So it's a big job. Becoming proficient at cleaning data and preparing it for analytics is a good skill to have. It will serve you throughout your career. And even though there are large language models in these days that will help you build the code behind doing some of this analysis, even then, it still needs your knowledge, your domain expertise to interpret what the results are, because it's just the machine at the end to figure out, does it still meet your needs? Is it still fit for purpose? So we still haven't found the magic technique that removes this effort from our jobs. So it's a really important skill to develop. And as you will see as we get into this, it's really big. There's, depending on what you want to do, you're going to be in Orion's galaxy, or you're going to be in the deep space or something, because there's so many techniques that you may need to get into your repertoire, your library of techniques over the years that you will need to learn. So this is something that it's an important space to probably try to keep up with over time with literature and knowledge training and courses in that. Okay, so let's start on our topic. So this is the agenda. We're gonna go into why we do have to do data quality. And then we'll talk about techniques. And because it's such a big space, the sort of the standard way of looking at data cleaning is to divide them into these dimensions. It's borrowing a topic from, I would say, the old world of data warehousing, which we don't do a lot of anymore, but the concept of dimensions is a good way to organize information, especially when it's techniques that you need to retain for quality. So we're going to go into what the dimensions are, and if you follow these dimensions, you will have good quality data. And then we'll talk about some design considerations. Quality doesn't stop with just cleaning one data set or figuring out one dimension on something. If you build quality in from the bottom up, then you will find that number 2 gets a lot easier. So we'll talk about some of that. Then we're going to go into a few advanced topics, which might be interesting and fun, and then wrap up. So first, why data quality? Common causes of data quality problems are really kind of in 3 categories. Humans make a lot of errors, or we might not intend to, but it just happens. The machines themselves will make errors, and then we might just be misinterpreting errors. So we're going to kind of talk about 3 big errors that have happened, and this will illustrate some of these common causes. Does anybody remember this? The Mars orbiter. So this was a major fail. This was many, I think millions of dollars were spent on putting this very important satellite up to Mars. And when it got there, when it tried to deploy, it failed and crashed, and we've never used it because of human error. One set of people were working in the metric system and one were working in the English system, and they did not know that. And so when they finally deployed it, the 2 pieces didn't work and it failed. So that's a data quality problem. Good example of human error. This is one of my favorites. This is Simpson's paradox. This is an example of the data is actually cleaned, but we are misinterpreting it. This was a UC Berkeley gender bias study, and what the university found when they were looking at this data is they believed that they were admitting more men into their system than women, and that they had gender bias happening. And if you look at this data, you could say, that looks like gender bias. But in fact, this is a summarization data error. If you looked closer and looked at the data in more detail, which basically puts a lens on the data, so you go down a little further, you found that in fact, women were getting admitted more successfully than other genders, but they weren't applying as much. They didn't have as many applicants. And so when they looked at this data differently and they went into a little bit more detail, they found that, in fact, they did not have that bias. And this is just an example of how the data could be clean, but if you're just looking at it, you might be misinterpreting it. And then this is a research project I did for a friend of mine who is looking into providing healthcare opportunities for seniors over the age of 65. And I was looking at our North Carolina County population data, and I see a miscoding error in one of the races. And this skews the data. It looks like we have two races. In fact, they are the same race for that particular population demographic group. And this is another example of an error that can creep into the data through miscoding or misinterpretation. So this is good examples of sort of 3 areas where you might see data quality problems. And then here's a bunch more that you will probably encounter frequently. Time series data sets. This is where you're looking at the daily totals of the weather. Sometimes there may be a daily total missing. And if you have a very large time series data set where you're missing a day that's dropped here or there, you won't know it. It'd be very difficult to find. It's a common data error. Or you might get data missing in a particular row or it's misplaced in a cell. I was recently working with a customer who is processing travel data. And travel systems have all these codes that they code into. So as you're going on a jet, you're traveling to city 1, city 2, and city 3. Sometimes they'll move those around and they'll put the wrong city into the data, and then it's miscoded. And it's actually had such that people were sent to the wrong city or their flights were delayed or canceled when in fact they really didn't need to be. So these kinds of errors happen a lot, especially when entering information into forms where humans are entering the information into forms. Using forms to collect data where you do a lot of validation. This is why when you go to like a hospital or a doctor's office, they're giving you a tablet and having you enter information in a form. That can give you a way to better validate the data so that it doesn't go into the system incorrect. You'll also see lots of invalid values, things that you didn't expect, correlated variables. If you're building models and you don't check the correlation between your variables, you can overfit or actually cause your models to be less efficient because you use 2 variables that really are capturing the same information. So looking for highly correlated variables, you may have pristine data, but depending on the target variable you're working with, if you haven't gotten rid of the extraneous variables you don't need, this can cause your models to be less accurate, less efficient. That also happens with having too many features to your rows. There's a rule of thumb in statistics that says you need to have so many rows for so many columns. Pay attention to those numbers because if you have too many features and small number of rows, you have to shrink that down. Statistically, that's going to cause problems in your models. Another example is using scale. So if you're working, I was recently working with a student and they were trying to do some weather prediction. And they were using the date, which is coded as a numeric variable, as a variable. in statistics, date doesn't necessarily represent a variable, and it has an increasing monotonic variable number. So each date that gets the next date is bigger than the previous one. That's going to tell the machine this is a more important number. So we will have to recode those variables so that you don't treat data that really isn't numerically important as a numeric value. Or you may have one column of data that has a 0 to 1 range and another that has a 10,000 to 100,000 range. Numeric values that are different in scales like that have different meaning in models and in reports. And so you may need to rescale your data so that you can more accurately represent that if you're using it, say, in a model. Some data just has low information value. There are algorithms to help you select important variables based on your target. Use those algorithms because you don't want to use variables that have no information value or very little information value. Drop extraneous variables. And then always, if you're doing models, check your assumptions. If you're doing linear models, there's assumptions around no relationships between the variables. You want to check that normal distributions are being, where expected, are actually happening in variables. So even if your data looks pristine, you still may violate the assumptions of the model techniques you're using, so check them. That's important to remember when working with data. Okay, so let's talk about.
People are always best friends. It's hard to feel wanted when nobody wants you. Are you listening?
Sorry, somebody's not on mute. Okay, so we're going to go into some techniques that can help you build good data quality. And these are dimensions. We're going to call them dimensions. There are really 6 characteristics of good quality data. And we'll go into each one of these. So the first one is completeness. A definition of completeness is the degree to which all the data that you expect to have is known. And an example of problems in this area would be data that is missing or data that is truncated. And so the simplest example is looking at a spreadsheet. This is air quality that comes out of the NOAA website in a particular Reedy Creek weather station, which is near our house. And we used this for our forecast, some of our forecasting algorithms when we're working with solar forecasting. And you can see that air quality numbers were just dropped, or the site name was dropped. Or there might be just missing information. They didn't gather ozone numbers in that timeline. So that's an example just of missing data. This is a plot that shows how the amount of missing data affects the success of a model. And you can see that depending on what type of data is missing, if it's in your training data set or it's in your scoring data set, your model accuracy can drop pretty significantly. So on the y-axis is model accuracy, and on the x-axis is the percent of missing values. And it depends on where the missing values happen and how they happen. If they're randomly missing, you might find that even without imputing or fixing them, you can still get fairly good model accuracy because they're just part of the training data, not part of the actual data that you're receiving when you're scoring. But if it hits the scoring data, then it gets more challenging because those are variables that the machine was trained on and expects, and then it won't be able to necessarily identify or accurately propose the target variable if it doesn't know what the incoming data has in it. Similarly, if you have systemic data or systematic data, this is chunks of areas in your data, perhaps a particular demographic or something that is dropped out, that can have very detrimental effects on your model. And so the worst case is when you have both missing data in your systematic missing data in your training and your scoring data. And you can see that based on the number of observations as you go out, model accuracy drops off fast. So it's just an example of how important it is to watch out for missing data, particularly if you're using it in a model case. So here's how you can correct for missing data. First, don't correct something you don't need. Check your variable's importance. If you've got a lot of missing data from one place, but it's highly correlated for some other variable that has a lot of good accuracy, then just drop the one that's less has less value in it, less data in it. Or if it really needs to be fixed, then we'll talk about what you can do that. But you should remove variables that have lower information value. And here's a place where I tend to go with SAS. So the SAS data mining techniques that we have makes it really easy to do an analysis for variable importance to my target and identify and actually automatically remove poor quality or redundant variables. You can do similar things in Python. You have to write a little bit more code, but this is a really good step to do before you ever start doing correction, especially around missing data. All right, so let's say you really do need that variable. How do I fix it? So the most common technique is to try to impute a new variable. So imputation means I'm going to inject a variable that represents what I thought would be on the line for that one. And you can do this in a lot of ways. So we have an MI procedure, and you can pick out which ones you want. There's even a way to pick the best, choose the best for me. But there's a couple different ones. You can choose the mean of the column, and that would be what you'd impute in. So, okay, I don't have a variable for the temperature today, so I'm going to just pick the mean. If you know it's an increasing value, you can choose the mean between the two variables around it. So I can take, okay, or I can pick the one that would be like the next most correct adjustment. Sometimes you can use a regression analysis. You can use regression to predict values and use the predicted value as the value to impute. Generative data is showing a lot of promise. You can use generative data to generate data and then use the generative data to impute your values for you. One tip is that after you do this, you need to check your distributions. Sometimes if you impute data, the original distribution, especially if it's randomly missing, may not match what your new distribution is, and so you need to maybe adjust the values to make sure that you get close to the original source. You can also choose to calculate missing values, especially if there's a lot of them. So if you know that there's a pretty simple calculation for something, don't even bother to pick up like the age value. If you have date of birth, calculate age. Don't even bother to do that. In fact, those are going to be highly correlated anyway if you're going to use them in a model. So maybe you choose one versus the other. If you're going to choose one, I'd pick age, especially in modeling, makes it an easier value to kind of draw conclusions from. And you can also use data standardization techniques. So I'm going to show you a little bit about what those look like. So this is an example of addresses. When it comes to imputing values that are things like names, addresses, phone numbers, you can't really do that. Sometimes the data is also poor quality. And so there are standardization techniques that we provide for standardizing things like names, addresses, phone numbers, imputing zip codes based on addresses, imputing area codes based on phone numbers. These are things that we can provide algorithms for to help you get, so you don't have to try to either drop that information or lose the information value. Now, these are all text fields, but they do have sometimes information value that you might need to use, especially location information value. I'll give you an interesting story. We were working with a group that provides data into the United Nations. It's called NatureServe, and they were getting address information for sensitive species that was sometimes the lat long values were miscoded and they were in the middle of the ocean, and yet they had address information in another field that they really wanted to get the information for. And so we used text mining techniques to geolocate based off the address where those protected species were. And you can use those using standardization techniques. A couple of other tips. Incomplete data is not necessarily missing data. A valid value may not exist, and sometimes it might be useful to know that that data was missing, such as I checked does not apply. Does not apply is a case that I need to retain in my data. And so sometimes this is where your domain knowledge comes in. You can put a 0 in there, or you can put a dummy variable in there for these kinds of situations. So it's good to look at your data and understand, should it be missing? And if it is missing, is that a valid use case that I want to retain in my data? And we already talked about dropping correlated variables. And then multiple imputation is a really nice technique to remember too, where you impute values based on other values that you are aware of. So you can replace several variables with something that you've imputed because you know that this is how my data is supposed to be produced. Okay, we're going to move on to the next dimension, which is uniqueness. So the definition of uniqueness, now remember, these dimensions are, if you follow these dimensions, you're going to have good quality data. So you should make unique data. There's only one instance of those values in the expected set of records. And it's not necessarily the whole row. You might have 5 rows of sales information, but each one of the sales that's relevant should be unique. It is a good indicator of trust. And problems in this data dimension are where you might have duplicate values. So here's a great example. This is back from my my solar energy data. One row was just miscoded and it came in twice. A lot of machine generated data may come like this. And so you should always deduplicate data that comes in, especially if it comes like from machine generated or sensor data. Sometimes it just gets recoded in a couple of times. You may find that you have duplicate values across multiple variables. And this is a little bit of a blurry screen, but this is an example of trying to deduplicate names or like customer or student information. We miscode it. Students miscode it. People miscode their addresses, or they may use their short name, Susan versus Sue, and they're still the same person. So being able to match and choose the best record, this is an example of like a multiple variable uniqueness problem that we need to solve. So for single record duplicates, that's pretty easy to do in Python. You can just have them in pandas, just drop the data frame duplicates and it'll figure it all out for you. In SAS, we have a proc that will figure it out for you and output the data set. You can also get the duplicates and see if there's any information value in those, just to be able to make sure you're not losing anything. Multiple records get a lot harder. And this happens a lot when you're combining data from different silos. So you may have researcher 1 that's giving you the data with a particular format for a code key, and researcher 2 might have a different format for the same code key. And so combining those gets to be a challenge. I work a lot with healthcare data. This happens a lot, even in the government that provides that healthcare data. They may be coded differently how patients leave the hospital. One system may recode it as 1, they go to a rehab facility. In a different system, 1 means they go to an outpatient clinic. So you do have to look in and figure out, this might require human interaction to be able to recode the data and figure out how they merge together. And then one of the techniques to put in your back pocket is using standardization and record matching. If you have variables that you know things can match on, use them, like names, phone numbers, other variables that you can find out what that is that can help you pick out what the duplicate records are and match on them. And we have techniques in SAS to do that. We have a generate match codes technique, which I think I have an example of it. This is an algorithm that will look across fields and figure out what are the common fields and generate what we call match codes. This uses a text mining technique, so we can do both fuzzy matching and non-fuzzy matching. using just distance direction for things. Casing matters in these worlds, so you have to be careful with that. So text mining, if you're going to do deduplication of this kind of data, you do need to consider use text mining, good text mining principles where you stem and you eliminate in extraneous characters and things like that. And then you can use that information to build a cluster. And here's an example of a deduplicated data set for a set of users. These are education information, includes like customer information on them. And that's what you'll get if you use these standardization techniques. There is a couple good papers, I put them in the notes, around record linkage in Python. SAS makes this much easier than Python, so whenever I have to do standardization, I tend to turn to the SAS tools, but you can do it in Python, and there's some papers that I've included in how to do it. Okay, we're going to move on to the next one, which is accuracy and validity. To me, this is the whoops factor, the wow factor, I call it. What is this dimension? This is describing how well the data verifiably represents the scenario you're trying to capture in your data. So here's where you'll find your inaccurate or invalid data. This is where you're going to find the Mars orbiter. The data was right in their two systems. It was just miscoded into a different value, an unexpected value. In some domains, it's critical that accuracy and validity are checked and are true measures of the data sets, particularly such in healthcare or finance. Nobody wants their credit card to be mischarged because some invalid value was swapped. Here's some great examples. Phone numbers are frequently miscoded. They might be too short where a variable gets dropped, or they might just have a variable number swapped. Another great example I see a lot is invalid birth details. People will put their birth information in and they'll miscode the year. And you'll just see invalid credit card charges. Happens all the time. Sometimes it's fraud, sometimes it's a mistake. So this is an example of validity problems where it's really important to check for. To check in this domain, you really have to have a domain expert. It could be a set of verifiable numbers that are coming from some place, such as a certificate or a lookup table, or it can be a domain expert that has that information. But in order to check validity, you really do kind of need some basis of truth that you compare against. The techniques for handling this are usually done through business rules. So business rules, which are things that require domain expertise, are generated to help check for these things and sometimes even correct for these problems. For example, you might have a domain of truth, which is your zip codes, and you can compare against this basis of knowledge called your zip code table, and you can use those standard tables as your lookups to compare against. There are companies that sell information like what are all the medical codes and all that, and you can use those kinds of data sets. There's a lot out there in the open source too that you can go out and look for that are just basis of truth data sets that you can use to compare against. This is our SAS Business Rules Manager. It's where you build business rules. We ship out of the box hundreds of them, but there may be ones that you can code up. This is a really common way for checking validity and accuracy. And we also have integration with a really nice Python package that we use in our own technologies called Great Expectations. And this is a Python package, and it has also 50 or so out of the box type rules that you can pick up and use. And it's really handy to put in your back pocket. It also does profiling, which we also use to check for distributions. So that it will check not only values, but is the distribution of your data correct compared to some expected data set. So you can generate rules based on your expected data set and then use those to check for validity or accuracy problems on some new data set. So it's a really nice package to check out. All right, moving on to consistency. So this one is okay, there's one that doesn't belong here, issue or dimension. And this means the definition of consistency is that data is stored in a similar way across the dimensions and records. Problems that you'll often see in this space are formatting problems, data stored at different levels of summarization, or data that just is mismatched. Remember my AN versus Asian coding error in our county data? That's an example of an inconsistent data set. And then this one below, I actually ran into recently for a small biking group that we do some work with to help them keep their records. They're inconsistent calculations. They have monthly revenue 70 and cost of 10, and somehow they're generating a profit of $500. That is just not possible. So inconsistent calculations happen a lot. It's actually something you can easily check for, especially if you have the data that goes into the calculation. You can write a business rule to make sure that you don't go over the expected values. And so how do you handle consistency challenges? This is going to start going back to the source of the data. You can put into databases in SQL Server or in MySQL or even in some basic Oracle, all the big databases, the cloud-based databases. You can put database constraints. If I have a person, I must also have an address. And that helps to make sure that bad data doesn't go into your system. You can use those calculated columns rather than using age as a variable that somebody gives you. Calculate it, and then you'll know that it's calculated correctly. You can create business rules. It's another place where business rules can come in handy, which would check your data to make sure that it matches what you expect. If you have a golden data set or a ground truth data set that you know is correct, then you can create the business rules from that and then use those on your other data sets. And then finally, a more sophisticated is to do anomaly detection. And we have several types of techniques that we provide for that. And you can use regression analysis to look for anomalies as well. We do that a lot when we're doing variable injection to generate variables, but that will also flag anomalies for us. Inside our visual analytics product, we have an extensive outlier anomaly algorithm that gives you all kinds of details on checking for outliers in your data. So use those techniques. They're really handy to look for completeness. But this is still a one-off. If you want to be checking it a lot, then you have to write a rule probably. You can also watch your models, and if your models start to degrade, this is a good place to look. There's also a really nice Python package that we've been experiencing, which is the Python outlier detection package, Pyad. And it has a series of outlier detection algorithms that you can play with, including some very sophisticated ones. And then the last dimension is timeliness. So a definition for timeliness is that the data is available within the expected time frame. So if I'm projecting whether my boat's going to be late, I probably don't want to look at data from 1912. I want to look at data from last week or something like that. So quality errors in this dimension would be stale or old data. Check that. I have worked with data sets that people have given me, and they swear, okay, here's my data, and it's 6 months old. If you're expecting data, especially in your domain or your problem you're looking at to be last week's data, check the dates on it. Sometimes it just comes in and it's just they didn't realize that wasn't the right data set. Or data's not coming in at the expected pace. If you're expecting data to be coming in every day and it's coming in every week or every month, maybe that you need to go back to the owners of the data set and say, can I get a more frequent data drop? And then of course our old friend of missing time periods. Definitely can miss time periods, especially in machine generated data. I've seen that happen a lot, and imputation is your friend in those cases. So here's some examples. I expect my data I want sales data quarterly, but I'm getting it yearly. I want information about my students' coursework daily, but I'm getting it monthly, that kind of thing. So systems produce data at different times. Sometimes that data has to get consolidated and the dates aren't matching up. So this is something you'll have to look at. Those machines generate different data. They may fluctuate in their drop of different data. This is a parts machine that was we were looking at recently that was generating, it's old data, but it was generating it. And about every hour, it would drop 3 records. And that was hard to find, but we had to find that and correct for that. So the impact of time in data that has timeliness problems is it prevents you from being able to, in some domains, tie back to the root cause. That every three variables being dropped, the machine had problems that were tied to that particular time window, and we weren't getting the records back on that, so it's difficult to figure out what the root cause for that was. Or it's hard to, if you have time data that's at different dimensions or different scales, it's hard to consolidate. It gets very hard to impute variables in those use cases. And so how do you handle it? So this is sometimes it's handling by going back to the source. Clean out that old stale data so you don't give it to people. If you're keeping it around, offload it, put it somewhere where people won't be able to find it. But basically get rid of it, get it out of your data system so that when the timely data you do, often see this. People don't put date timestamps into the data, or they'll put 5 date timestamps into the data. Try to say, okay, if you need 5 date timestamps, put one close to ordinal position 1. And most people will assume that's the one that they would use for most of their research. But make sure that your data does have a date timestamp if it's timely data that you need to incorporate. It's just in generally a good practice to have that in your data. Standardize on your time collection periods. If you have a sales system and a supplier system, try to standardize on, talk to those 2 teams. Can we standardize on the time data collection that we're going to use? So that when you do inevitably have to join your 2 data sets, you will have already thought through, okay, can we standardize on these time ranges? Of course, there's always using business rules after the fact to watch for those errors. And we do have some algorithms that will detect and correct time series problems. All right, I've been talking for a while. I'm going to take a little interlude here and give you like a minute, or if you want to go get a coffee or something. Here's the question. So Roman concrete has survived many, many centuries. And their engineering is an amazing feat. And so some recent studies have been done to understand why it's so durable. So why do you think Roman concrete has survived the centuries? And you can put it in the chat, and if you want to take a 2-minute break, we'll come back at 11:45. right, everyone, welcome back. Nobody picked aliens. All right, so in fact, it is tiny impurities in the concrete. This is a fascinating study. This is a case where a little data quality problems actually helped in the overall strength of this particular material. Some recent research has found that there are small impurities in the actual concrete that causes it, as it settles, to close the gaps and be able to handle the settling. And so I love that self-healing. That's just an example of an architectural or a materials specialty that actually makes the overall material stronger, which essentially is a good design principle. And so that leads me into my next part, which is good data quality starts with good design. So we're going to talk about some data quality things you can do that are good design principles that will help prevent some of the problems that you may see with quality. Okay, so I'm going to go through some tips first. So there's an old paper called Tidy Data, which is really like a Bible for some of the tips to put into your toolbox of good data principles. So I have a link to it in the notes that you can go read about it, but and R has I think a already built-in algorithm you can use to just call it. But essentially, here's some of these tips. Column headers need to be variable names, not values. And this is a great example of a miscoded data set where we have the data is actually in the rows and the column headers are the data. So that the data is miscoded where the column headers have like the actual values in them, and then they've miscoded the columns. So you really want your columns to be variables, not the data. And a sort of a side piece of that is try to make your variable names easy to understand, because you may not be the only person who will ever use that data set, or you may have to come back to it 6 months from now. So just naming your data in a way that you can use it and understand what it means will help prevent quality problems in the future. Similarly, don't store variables in one column. Don't store multiple variables in one column unless you really need the data that way. An example is Smith, Peter, where you're putting the name in one column. That's fine if you need to do it, but you could always build that data, concatenate columns to do that if you need it. So try to keep each column unique in what it's storing. And then every row should be an observation. You shouldn't have observations one observation that spans n rows. Couple other tips: use database constraints. They're really handy. So that's the one I gave you. If you have a name, it must have a zip code or a phone number. They will also prevent you from putting missing values into data where you expect to have a value. So if you expect to have a student ID code in a data set, put a constraint on it. This is a primary key. And then the database will not accept. It will reject records that don't have that value in them. Use a single date column to represent a record date. If you need multiple records, dates in your record, it's best to just like have one. Okay, this is my record date, and then okay, I took this sample on this date and it was analyzed on that date. You can have other dates, but it's really helpful to have a single date that sort of represents the ground truth. And then don't accept the data set as is. You may need to rescale it or recode it based on what you're trying to do with that data. So it's good to have a repertoire of processes. Like I have a little library of SAS macros that I keep, and I just reuse those. If I need to rescale, I just rescale right there. If I need to recenter, I'll do that. So as you're building these little algorithms, keep a little library of them. If you need a Python library of something, you will use these basic sort of preparation techniques over and over again. Eventually, if you do this a lot, they'll become sort of second nature. Really handy to have a primary key. Don't rely on row order. Databases will definitely, in order to optimize storage, mix those variables up. And you may not always be in Excel. You may be in Excel today and tomorrow you need to be in SQL Server or something like that. Or you're going into the cloud where there's like only databases. So put a primary key in there. And tip, if you're using any kind of parallel processing systems, sequential values do not work really well. A UUID is a really good idea. It's just a large character string with numbers that is unique across all kinds of dimensions. So sequential values are fine to understand, and you know you're not going to have hundreds and hundreds of thousands of records. But for any big data use case, you really need to generate a unique ID. And databases will do that for you. And then this will help all of us data scientists that are using your data. Add descriptive information to the data set itself. Use labels, descriptions, any place you can to give a little bit more knowledge about what that data has in it. It'll help us and it'll help you when you have to come back and use that data. Just an example of recoding. I see this a lot, and our algorithms will actually do this for you, but if you have to do it yourself, just be cognizant of it. Data that is coded as numbers is not necessarily numbers. If it's truly something that's just a nominal value, but it's coded as like 1, 2, and 3. I see this with, let's see, where do I see this? Nationality. You'll see they'll code white 1, black 2, Asian 3. They have no numeric value. You really do need to recode those if you're going to use those in any kind of model where you can say black, yes or no, Asian, yes or no. And that's called dummy variables. They represent your data, but just be aware if the data is a numeric value but has no numeric value to it, you'll need to make sure you recode it. And that's called dummy variables or one-hot encoding. Happens a lot in demographic variables. When you get data that has duplicates, you survive, and it's something which has like data that you know needs to be down to a single record to represent something, like an address list or a name list or something like that. You do need to do deduplication because otherwise you'll use Susan Woodward's 5 times and it'll be different. The machine will think that's different Susan Woodward's, but it's really the same one. And so that's called surviving record analysis. We talked about that just a little bit earlier. That's an important technique to put into your toolbox if you're working with this kind of data. Again, demographic data is common for this. All right, let's talk about different data set design principles. So if you do need to flatten data, let's say you get a student table and an account table, or a customer table and account table, and you need to combine them. This is a case of transposing data, and the transpose function is your friend. And you can do that in Python, you can do that in SAS. This is an example of combining those 2 data sets into a single data set. We'll use this kind of flat data set a lot if you're building reports. So prediction of events, you'll use these flat data sets for things like a campaign, or if you're doing time series models on a single sort of target time series. We use this kind of model for our solar array predictions, and we flatten it out. If you're doing cluster segmentation, so you don't really want 10 patient records of all of the same patient, you'll need this sort of flat data set. And then for reporting, I was just doing this on a place where I had these very detailed records that were in 5 rows, all about the same variable. And so I had to flatten them all out. This is how you do it. You'll take the subject, the table, and you'll take the observations that have the multiple values for a single variable, and then you'll just put them all at the end. And so you'll turn what is a long, skinny data set into a short and wide data set. And there are techniques to do this in both Python and SAS to help you with this task. And sometimes you'll have to aggregate, but be aware of Simpson's paradox. If you do have like household and customer and credit card and there's like 10 transactions, you may not need the level of every single transaction, which would make every single transaction on a column and make that a really wide data set. So you can sometimes summarize. Maybe I just need the credit cards transactions for today at this household. And so consider summarization to help you build that wider data set. Analytical models that do well with this, regression models, talk about time series, survival analysis, analysis and variance, some of these model types. Okay, multiple rows per subject. So this is a patient comes in and or this is an example of a person comes in to a bank and they have their checking and their savings accounts, or a patient comes in and they have 5 procedures that they do. So that's a multiple rows per subject example. You'll see it a lot. Market basket analysis. This is an example for customers. They come in and they buy baguettes and herring, or avocados and artichokes. This is a common example where you really do need multiple rows per real transaction. Weblogs is another example. I come in and I'm clicking through my Amazon account and I visit the clothes and the shoes. We want to retain that information. That's called a customer journey. We want to know what's going on in that customer journey. It's very valuable to us. And so for that kind of data set, you still might have multiple tables somewhere, but you're going to turn them into this multiple row per transaction model. So you'll use this when you're looking at things like market basket analysis, or you're trying to do association analysis, where you're watching the customer comes in and they go to 5 places and I want to know that journey. Where did they go when they visited my website? If I'm doing time series analysis and I have different subjects, so I want to do time series analysis on my solar array, and I want to know what happens with the weather patterns, that kind of thing. Sequence analysis is another example of that customer journey. So just a quick summary there. Good design can save you time. Think about these best practice principles based on the problem you're trying to do. And if you apply them, you will be able to build something that can withstand some of the challenges that you will have in your models or in your reports. All right, we're going to move on to the final area, which is advanced topics. And these are things that can help you, that are sort of bigger things. They can help you maintain quality over time. So here's one of our favorites. Who are you going to call when you need new data? Google Datasets is your friend. So you sit down. This is from a presentation on data catalogs that I went to at a couple years ago out in California. And basically, when you that Lyft did, and when you sit down to do research, how do you find your data? So Google Datasets is a great source of that. You can use Kaggle for data. There's a number of repositories of data. And of course, on the internet now, it's a lot easier. There's repositories where researchers are putting out their data, which is really handy. But it's still a challenge because you got to go find that data and you got to go figure, is this what I need? And what else do I need? So where does that data exist? Where is it? Was it sourced ethically? Big important thing to think about. Do you have access to it? How can you use it? Is there private information in there, or is it sensitive information in there? Can I trust it? This is one of the big challenges when sitting down to work with data. And fortunately, the industry has come up with a really handy feature set or product suite to help you do that. And this is from one of the big analyst companies, Gartner, who recognized sort of this phenomenon that was happening in technology around coalescing around this concept called a data catalog. And it is probably one of the most valuable things you can have if you're working with data on a site where you have like more than, say, 100 data sets. You really need to think about a data catalog because it will unlock the power of your data across whatever enterprise you're in. And what do? They help you find and identify useful data. And they provide the ability to both govern it, ensure that it's protected, and share knowledge about that data across the system. And so Lyft has one and we have one. Data catalogs capture metadata. They'll tell you things about the context of that data, how it's being used or how it should be used, where it came from, where is it going, and how it changes over time. Metadata is really important in the world of big data systems. And so this is SAS's information catalog. This is my product. This is what my team works on. And it is, as a researcher, we use it all the time. And our company uses it quite a bit too. But basically what it will tell you is what assets you have in your system. It has an intelligence search. We use OpenSearch behind it, which has nice search ranking, and it has the search helps and stuff. And it'll just tell you about all the data in your system. How good is it? Goes down into details across multiple languages. So it's the Chinese data set that we have. Our algorithms can pick all the patterns out even in different languages, and we support 30 languages. So if I need a data set about address information or student information in Spain, which is what I needed a couple months ago, I can go here and look up, is there any student information in Spain that I have access to? And sure enough, I get that data set. So it's a very handy thing. There's a nice open source one, much less robust, but it is out there that the Linux Foundation sponsors called Edmondson. It's actually the one that Lyft donated. And it has the basic techniques in it, and it's handy. Even if you don't have our tooling, if you have access to something, this is a good one to check out. Data provenance. Let's talk about that. So this is getting more and more important every year as we build out these large language models to make sure that we are using ethically sourced data. And being able to tell where data has come from and where it goes is really important. And that's called lineage or data provenance. It will tell you things like, where does data come from? Where does it go? In the industry, we have lots of tooling for this. ChatGPT, our friend, it's a privacy nightmare. And as you can see, it's in all the news. Not all the data that was used to train that model was ethically sourced, or even people were aware that it was being used at all. So it's going to be, watch what happens in the news cycle and watch what happens with these large language models. It's an interesting time to be here with this information. So people are looking at how to figure this out, and Lineage helps. This is our Lineage data viewer. It will tell you where data has come from and where it goes. It integrates with open source tools like this one. This is, I think this is Open Lineage, which has a number of vendors that we all supply data into. So this looks across the systems and can tell you the lineage sourcing across systems. Most large enterprises and even medium scale enterprises that are working with hundreds of data sets have some sort of data provenance data lineage viewer, so they can track the lineage of data. So they have a data catalog and they have a lineage viewer. License compliance. This is a big deal. This is something that the foundation, Linux Foundation, has been looking into, and I've also been working with the SAS lawyers on. And this is about, where's the data coming from? These large language models, we don't always know. ImageNet, we don't always know how that data was trained. And so this is something that the open source community is getting involved in, the foundation's getting involved in, and even companies like SAS are getting involved in, trying to make sure that we are we're using data that has been sourced in a way that is compliant with all privacy rules and all copyright rules, and also making sure that we're using in a way that it's expected and that people know it's being used. So you can watch this space too if you have an interest in it. It's something that we are actively involved in because we want to be a company that is sort of pushing the envelope in ethical AI. Data drift. This is a real problem. You probably have seen this with your models. It's definitely a problem with your data. And it's something to think about, especially if you're acquiring data over time. And there's kind of 4 areas of data drift. You might see a sudden shift. The data distributions change, or it's gradual. One record comes in slightly different than the others, and then 2 come in, that sort of thing. or it's just changing over time. The people who are buying my products today are not the people who are buying my products 6 months from now. So that demographic has shifted. Or it might be like in our solar energy, every January and February, there's a 10% drop in our generation, and it's just a recurring concept. So this is called data drift. It's something that you do not want to be aware of, especially if you're using these models that you have over time, or if your reports are reporting something over time, something you want to be cognizant of. It can generate a quality problem that you might not see right away, but can definitely degrade your model accuracy or provide invalid information in reports. And so fortunately, there's ways to check for that. We have tooling in SAS. We have monitoring those data rules that you have. We have monitoring capabilities to turn those into a nice little dashboard that you can watch for data drift. There's a job family called data stewards. It's their job to watch for things like this. And they'll monitor your data. If you have lots and lots of data, you probably have somebody doing the job of a data steward, even if they don't have that title in your area. They should probably be watching for data drift on data, especially if it's mission critical data. And then there is an open source product that is in Python that we've played around with that helps with data drift detection, and it will give you little metrics about, okay, this thing is, reports are doing it. But just be cognizant that even if you've got all your data right and it's beautiful and clean today, it may not always be that way. So you do need to monitor it over time. That's kind of the point of watching for data drift. And then curation. This can unlock the power of your data. So think about what curation is. It's the process of gathering relevant information to add value. Libraries are data curators. They curate all the books that come in and they make sure they get to the right shelves and they're useful so that people can find them again. Same thing can happen with your data sets. Data curation is the process of applying expert knowledge to your data. So sharing information about usage, sharing information about what is in the data set, telling people this is a good data set, that's a bad one. That's another job that a data steward frequently does, and it's a really important job if you have a lot of data. It also allows you to crowdsource knowledge. So in our catalog, we have a place where curators can go in and annotate data set information with, this is how it should be used, and this is where it was sourced from, and this is the license that we built from. It was built from. Here's the compliance. So when you sit down to use that data set, you'll have all that information at your fingertips. There's also a status field that lets you say, okay, this is a good data set, this is a bad data set. And you can actually, in some cases, people will even put this stuff in through a workflow, a business process, which says, okay, I want to onboard these 5 new data sets. And they'll force curation to happen on those data sets before they unlock it for everybody to use. Getting a little away from that now because everybody wants their data today. They don't want to wait for the curators to get in there. But still, somebody can always go behind and curate that data for you. Even if you're using it, you can go in and add that information for the next person who wants to use it. So information catalogs capture that kind of data, and it can really unlock the power of your data. And then finally, we'll talk briefly about bias. So this is something SAS is spending a lot of time researching, and we have algorithms to detect data bias in models, and we're working on algorithms to do earlier detection of data bias. But there's things you can do now, even without specialized tooling. You can watch out for protected groups. So if I read a really great paper recently about how to beef up the signal for protected groups that have very small number of records. The Native American Indians, we don't have a lot of COVID data on their experience with all the COVID shots and all that. And so being able to detect that data is missing for that protected group and beef up the signal is an important aspect of bias detection. So look across your protected groups, make sure that they're represented well. And there are techniques for increasing the signal there if you need to. Experts in domain knowledge can help with feature engineering to make sure that they know what's expected from the standpoint of the data, and they can sometimes just spot bias in that data. It can start way back at the beginning. Make sure that you're using fair and unbiased data collection strategies. Don't just go to one neighborhood in a town. Use a distribution that blankets multiple neighborhoods. That's why the census goes out to so many different groups, to try to make sure that they do fair and unbiased data collection. If you do have data bias, it's much better if it's random than it's systematic or systemic, because you really do want to make sure that you're covering randomly bias. You don't have bias creeping in that's like in a particular area. You can do techniques. There are some really interesting techniques now available for doing resampling or augmentation, generative data. Cross-validation can help beef up the signal. So these are just some techniques that you can go off and research to help you mitigate bias if you do need to mitigate it. But at first, it starts with just detection. So you can watch for it in your data. You shouldn't wait till it's already in your models before you're checking for data bias. All right, long journey. So we'll wrap up here. As you can see, data quality is a big space. It spans lots of different areas. It has lots of different domains, but just remember, starts with, you can look at those dimensions and check for data bias across those dimensions. You can ensure better data quality if you think about data design up front. And then there's some more big tools, big capabilities that are out there that can help you keep your data clean and pristine and find it and use it better when you need it, more high quality data. I do want to point out that I mentioned that we have access to SAS, but we also have some great SAS classes. We have classes on Coursera. I'm a big user of these, of the open education systems. I got edX and Coursera. I use both of those. We have a great training website. And then that statistics class I mentioned, it's a really good one if you want to just get a reminder, refresher in statistics. It's very well done. And then we have lots of tutorials and our On Demand for Academics, which is our free access to SAS software. If you just want to go around and play with it, that's down there at the bottom link. Okay, I am going to turn it over for questions, and hopefully this was helpful.
Do you have any guess on how much that 80% number might lower with some of the tools you were talking about, some of the ways of improving and automating that data cleaning?
Definitely the finding part. Information catalog has changed information catalog has really changed the equation. And all the companies that have them will tell you that. That used to be, there's actually a chart in there about that. Beginning up here. This one right here. So collecting data sets, that's like 20% of the job, definitely 20% of the job. If you have a catalog on site and everyone's contributing information into it about the data sets they're using, that can cut it way down. Some of the cleaning side of it, particularly like the recoding and the detecting important variables, that's an important thing if you're doing modeling. So that can really help over here. Maybe that can cut off like 10% of the job. And I use our decision tree algorithms a lot because I use a lot of this data that isn't necessarily numeric data. And it handles, data that's got lots of issues in it. And in that one, our decision tree, it does a lot of the recoding and analysis for you. So your variables you don't have to worry about. That has saved me hours. When I have to work with students that don't have access to it, it's like, oh, really? I have to go back to the Python decision tree. So that can save you a lot. There's a reason we spend a lot of money in building out these tools. definitely can help you maybe cut off, I don't know, 20-30% of your job. Having a data curator can also help. Somebody whose job it is to help curate data and unlock it for you, that's another big time saver. Sorry, go ahead, next question.
Nancy, is there any specific course within SAS you would recommend, either with Python or with SAS within your collection that focus more on the data cleaning?
We do have classes. We have a data science curriculum, and we have classes that will take you through the cleaning side of it, and both cleaning for modeling purposes and cleaning for reporting purposes. And if you go to that website that has all the SAS classes, you can see them in there. There's also one for around text mining. Text is kind of its own special thing. And if you do deal a lot with text, you might look at that text one.
Thank you.
I think Tom might actually be covering the text mining. He's covering it as a topic later this summer, and I'm sure he'll recommend the appropriate class. I'm going to put the link to the SAS Academy for Data Science in the chat, though, for anybody who's interested in that data curation course.
Other questions? Does any of this bring to mind thoughts about problems you've run into, techniques you've come across? Other questions?
Yes, thank you again, Nancy. Since we have no questions, so I will share the recording and the PowerPoint presentation, of course, on our website. I appreciate all, all the knowledge you gave us today about how to maneuver, especially with the new trend of checking biases. That's a new dimension added, like I never in the past was, paying attention to those aspects. So, so thank you so much for this wonderful presentation. Thank you.
Thank you for giving me time to share this information.
Thank you.
Appreciate all your time. Hope you all have a good rest of your day.